The third application example is a boost converter. We have introduced the buck converter in lecture 54. That is to say, we can transform DC voltage from 5 volts into 3 volts. Here, we will introduce how to transform DC voltage from 3 volts into 5 volts DC voltage. It's a second order circuit, which needs inductor, capacitor, diode, and a switch. The switch has two working states. Between D and S, it's either short circuit or open circuit, which depends on the voltage between DS, high level or low level. So we can draw a subcircuit for the two working states. It's like this. When D and S is a short circuit, the diode withstands the reverse voltage drop, so it's open circuit. The whole circuit can be divided into two unrelated subcircuits. When GNS is low level, DNS is open circuits. At this time, the diode conducts. The whole circuit is such a state. Next, by using the engineering viewpoint we introduced in lecture 55.4, let's analyze the voltage of the load. That is the voltage of the resistor R. In the engineering viewpoint, we consider the inductance to be very large so that the current is a constant value, and the capacitance is very large so that the voltage is also a constant value. We assume that the duration of the first state is T on and the duration of the second working state is T off. If the current entered into the steady state, then for the energy storage element inductor, the energy stored during T on is equal to the energy released during T off. Okay, we calculate it now. If you want to calculate the stored energy during T on, it needs to set such a reference direction for the inductor. That is to say, during the period, the energy stored in the inductor is Us times I times T on. In the second state, if you want to calculate the energy released by the inductor, it need to set the non-associated reference directions for the inductor. In this case, the voltage needs to get by this path. So during T off, the energy released by the inductor is U minus Us times I times T off. In the two states, the energy absorbed by the inductor and the energy released by the inductor are the same, so we can get that U equals Us times T over T minus T on. Let's divide the right numerator and the denominator with capital T and find that it's equal to Us times 1 over 1 minus capital D, where D is the duty cycle. D equals T on over T. That is to say, the greater duty cycle is, the greater voltage of the load will be. Next, we use a simulation to verify the derivation. Please check the circuit on the screen. That is the circuit of the boost converter in the previous theoretical analysis. Channel A of the scope is the voltage between D and S of the MOSFET. Channel B of the scope is the voltage of the load. We now have a look at the duty cycle. Here's a 50%. We simulate. You see? The input voltage is 5 volts. Channel B is 10 volts per dive. That is to say, under the condition of 50% duty cycle, the output is a smooth voltage of 8 volts to 9 volts. Next, we change the duty cycle to 80%. We simulate again. You can see that after we increase the duty cycle, the output voltage changes into 13 to 14 volts. Through the simulation circuit, we can find that the boost converter realized the increase of the DC voltage well. In previous lectures, we have introduced the 3 practical applications of the second-order circuit. There are lots of applications of the second-order circuits. We will continuously introduce in the subsequent lectures. Okay, that's the end of this lecture.